we have this handout link for you. An improper integral, you're either going to see an infinity attached to it, or there's going to be a point of discontinuity either at the endpoints of that integral or in the middle of that integral. Think about if you have a vertical asymptote, you can't integrate straight through a vertical asymptote. And if you're using it to find an area, you couldn't integrate straight through the vertical asymptote there. You got to break it up into separate chunks. Please model these examples, notation, everything. Notation is pretty important. You want to make sure you're getting all points possible on an AP free response situation. Sometimes if you're lazy with that notation, you end up plugging in wrong stuff and you forget to do something, or you plug something back in wrong and people miss stuff, on a testing situation there. So for the homework, let's develop good habits, model these examples, practice that notation, especially that very first step there with that limit notation with the integral. So if you have an improper part, you need to remove the improper part. So these first two examples, we see this infinity attached to your integral. That's the improper part. It's very easy. These are very simple problems here to remove the improper part. All you do is you remove it and replace it with a letter. If it's on the bottom, I'll use an A. If it's on the top, I'll use a B. So notice I remove the improper part, that infinity. I replace it with a B, and then you do the limit as that letter approaches that infinity that you just removed. All right, so then that's the most important thing right there at the beginning there is just get that first step down with that notation, and then you should probably have a pretty straightforward integral right here. I integrated the 1 over x, I got the ln of x, and then we have a definite integral. So plug in the top number, the b, plug in the bottom number, the 1. The ln of 1 we know is 0, and then you get the ln of b right there. So when you carry down your limit notation, when you plug in that infinity for the b, you have the ln of infinity, and it's very helpful to know your ln graph right there. So if I have to do the ln of infinity, my y's keep getting larger and larger, that answer is going to be infinity. If I ever have to do the ln of 0, that's going down to a negative infinity. If I have to do the ln of 1, that's equal to 0. So it just kind of helps us to kind of know what that graph looks like. Now in this section, whenever we get infinity for an improper integral, what our actual answer is going to be the word diverge, okay? We're going to fine tune that in the next chapter where we talk about what makes an infinite series converge or diverge there. So right now, if you do your normal integral, if you get infinity, just put diverge down. This next example right here, you have the infinity, so same exact thing. I removed the infinity, replaced it with the b because it was on the top, and then I did the limit as that b approaches that infinity that I just removed. So please get that notation in there right there. That's gonna help us out in the future. And then you do your normal integral. When you integrate e to a power, you're gonna get e to that power, but you gotta balance that negative. And then what I like to do, strongly suggest you do here, because sometimes people are gonna put diverge down when they shouldn't. Get rid of those negative exponents first, like we've been doing all year. Get rid of those negative exponents first, and then do your definite integral, do your fundamental theorem of calculus, plug in the top number, plug in the bottom number, and then right here, so like e to the 0 is 1, you get +1 right there. But right here, because sometimes people will plug in, like right here, they'll get this negative e to the negative infinity, and they're going to put diverge because they think that's an infinity. That's not right, okay? So if you get rid of those negative exponents, and then you're plugging in that b right there, and now you're going to do the limit as that b approaches infinity. So when you do 1 over e to the infinity is infinity, and when you do 1 over infinity, that's going to be 0. So 0 plus 1, we're going to get 1 for that. All right, so we're going to fine tune this next chapter, right? Not the most important thing, this right-hand side right here, but I just want to talk about how you can't really tell just by looking at it whether that answer is going to exist or is going to be diverge, right? So this first example is 1 over x, and you're doing like an area from 1 to infinity. You're thinking, hey, it makes sense it diverges because this area just kind of is an infinite area, just kind of keeps on going on forever and ever and ever, and we got diverge for that as an unbounded area. But if you actually graph this one here, it's a similar situation where you do kind of have like an unbounded area, just keeps on going, but we're actually able to get an answer for that, right? So we're gonna learn converge and diverge next chapter, okay? And we'll learn all these different things of what makes something converge and diverge there. So we'll do that. I just want you can't tell just by look. All I can tell you right now is that this thing approaches that x-axis a lot quicker than this thing right here. And so it's gonna narrow down a little bit faster for us. And so we're going to get an answer for that. But don't worry so much about that now. I just don't want you looking at a graph and think, oh, that's an unbounded area. That answer is going to be diverge. Doesn't have to be. Sometimes we're able to get numbers for that. So we'll do a whole chapter with that next chapter, right? So please model that notation. Those are easy integrals. You just got to get that first step done with the notation. You don't have to write that limit notation down every single time, but just make sure you bring that back in at the end. All right, this one here, think about if I test you this chapter and you see an integral here. Common mistake is students just treat that like it's a normal chapter 4, chapter 5 integral, integrate it, plug in the 4 and 0, and they get the wrong answer. I can't give you any credit when you do stuff like that. So you got to think, if I give you an integral, if it looks simple, think, is this an improper integral right there, right? We're going to test you over these indeterminate forms and these improper integrals this chapter. So the reason this was an improper, right? I don't have an infinity there. The 4 is okay. I could plug it in for x. I could plug anything in between 0 and 4 for x. The reason this is improper, because just take the bottom and set it equal to 0. The bottom is equal to 0 at x equals 0, and 0 is part of that integral. So that's why it's improper. Okay, so the 0 is the improper part. Remove the 0, replace it with a letter. Since it's on the bottom, I'll replace it with an a, and then I'll do the limit as that a approaches that 0 that I just removed. So that's how you handle the improper part. That's perfect justification, perfect notation, where, you know, we get perfect full credit for everything on an actual AP test on the free response. And then when you integrate 8 over x, you get 8 ln of x, and then you can plug in the 4, you can plug in the a, you can do the top number minus the bottom thing. And then now you're going to do the limit as that a approaches 0. So this 8 ln of 4 is a number, but when you plug in a 0 here, all right, the ln of 0, that you got a vertical asymptote at x equals 0. So if you do the ln of 0, you're doing the limit as that a approaches 0. So as we approach 0, that's undefined. That's going down to a negative infinity. So since you get some sort of infinity, if you do your improper integral, you get infinity. That's when we're going to put the word diverge down. All right, the next example right here. Very important. You got something just like this in the homework. Please model this. Not a normal integral. This is improper because it has a fraction. And if I take that fraction, I set it equal to 0, I get x equals 2. And more importantly, x equals 2 is smack dab in the middle of that thing. So the first few in your homework just ask you, is it an improper integral or not? So all you got to do is look at it. If you see an infinity, say it's improper because of the infinity. Or if you see a fraction, say it's improper. You might have to like factor and set it equal to 0, right? But just take the denominator, set it equal to 0, and solve for x. And if those values are in that integral, that's what makes it improper. If I had the integral, if that was an x minus 15 in there, and I got x equals 15, that is not an improper integral. That would have been a normal integral between, because 15 is not in between 1 and 4 right there. But my improper part is the 2. So what I like to do, I like to write it like this, is I'll do the integral between 1 and 2 plus the integral between 2 and 4, and I'll remove the improper part on both of them. So I'll remove this top 2, I'll replace it with a b, and I'll do the limit as that b approaches 2. And then I'll remove this bottom 2, I'll replace it with an a, and I'll do the limit as that a approaches 2. So this is what I gotta see this. If I give you something like this on a test, this is what I'm looking for. First step right there. If you don't have that, you do not get full credit for that. So make sure you perfect with that notation. Practice that in the homework right there. Right? You're not going to get full credit on the homework if you're not careful with your notation there. Now, here's the thing: when you have two separate things, you don't do two separate things unless you have to. Okay, I'm sorry, you're going to do two separate things, but here's the thing right here: you're going to do one at a time. Okay, you don't do the first one, get infinity, and do the second one, do infinity, and do some weird with indeterminate form. You're just doing one thing at a time. This is one section of a graph, because if you graph this thing, it has a vertical asymptote. And if you're just thinking, can I get something from the left side? Can I get something from the right side? If you can't get an answer for both of them, the whole thing is going to diverge. So basically, you just do one at a time. If you get an answer for the first one, you do the second part. If you get diverge, if you get infinity or diverge for either one, you just stop right. If you get infinity for that first one, just stop right away. Don't even bother doing the second one. The answer is going to be diverse. So if you get infinity for either one of them, that's going to be diverse. So I did an integral here. That's just a u raised to the negative 1/3. So you should be good with integrating that. Plug in the b, plug in the 1, and I'm in this right there. Right. So notice that you integrate, plug your x's back in, and then you're going to get this 0 minus 1. So a lot of times these look messier than they actually are. So when you integrate it, plug in your numbers, and then remember to do your limit at the end. So now when you plug in the 2, you're going to get 1 to a power minus the 1. So you're going to get 0 minus 1, which is -1, you get -3/2 for that. Now, since I didn't get infinity right there, then I got to keep going. I got to do the second part. But had I gotten infinity, then I'm going to just put divergent. Don't even have to do the second part. But then when you do the second part, this is the same integral. And this time you're going to plug in the 4, then you're going to plug in the 0, and then you're going to get these weird looking numbers right there. And so you actually do get answer for that one. All right, but just be a little bit careful. Just be on the lookout for those. Please model these examples there. It should be a pretty straightforward section. You may have a couple harder integrals. You might have some trick stuff in it. You might have some integration by parts, but you know how to integrate every single thing. We're done learning integral techniques. There's nothing new how to integrate it. The only thing new is the very first step there, getting that notation down and dealing with those limit answers there. Got a couple nice quotes there. And in this example, I just put in as a bonus example, just because when you have that a squared minus u squared, that's your arc sine pattern right there. And sometimes people forget those. So make sure you look over your blue sheet review. And then when you do the arc sine, when you plug in the b, plug in the 0, and then you're going to do arc sine of 1, right? Which is pi over 2. That's the angle whose sine is equal to 1, which is your pi over 2. You might have like arctangent of pi over 2 or arctangent negative pi over 2 and stuff like that in the homework there. So you got a few things that happen with the trig, but we'll talk about that as we're going through some questions there. So just do the best you can on that. All right. Thank you.